Hola, hola. ¿Cómo están? Estamos también por nuestro canal de YouTube, disponibles ahora. Estoy buscando la URL, no sé por qué no la puedo ver. Sí, ahí está. Vamos a... Buen día a todos los que se van uniendo.
Hola,
Desde
hola.
temprano. Tenemos los Pato López también. Don Andrés, ¿dónde está don Andrés?
No se le ve.
No se le ve. No sé por qué no me da la opción de... Está entrando don Guido, ahí está entrando don Andrés. Don Andrés, ¿está por ahí? Buenos días, Guido. Andrés, ¿está por ahí nuestro moderador?
¿Yo?
Sí, pues.
¿Siempre?
Eso, muy
Podríamos
bien.
rotar.
Salud, muchachos. Una rica taza de café. Sí, buena taza, Guido.
Está helado ya, pero bueno, está helado.
Está helado, Juan. Oye, Yamira, ¿está por ahí?
Sí, le mandé el link y dice está conectando.
Ya, buenísimo. Entonces, todos tenemos que speak in English.
All the rato.
Alterat. Beautiful.
Como los meetups de verdad, po.
Ahí estás diciendo que entonces nuestro mira no es de verdad.
No, no,
¿Eso
no.
quieres
Como,
decir?
como los otros, po. Como los más internacionales.
Ah, bueno. Estamos también por primera vez en vivo en nuestro canal de YouTube también. ETHSantiago, Ethereum Santiago, pueden buscarlo. Así va a quedar disponible de una el video para aquellos que quieran revisarlo nuevamente. También, bueno, para los que saben, tenemos nuestros POAPs. El último todavía está en proceso, no ha vuelto aún G-Way el gas, así que tenemos que esperar. Pero está en la transacción ejecutada, así que en algún minuto va a llegar. Y Guido también va a pasarle a todos por privado el link para el POAP de este meetup. Peter está preguntando por Slido,
Ya
don
voy,
Andrew.
ya voy, ya voy.
No jodan, es muy temprano, dice.
¿Les gusta el slide? Ya, ok.
Ahí viene Amira.
Hello, everyone.
Hi Amira, how are you?
Hi, doing well. I'm sorry, the
Ahí.
last one to
Awesome.
join. I hope I'm not the last one to join.
No, don't worry. We have like 5 more minutes to wait for the late ones.
Okay, perfect. I will turn my camera on. Hey,
Hi Amira.
Hi, Amira.
so we have people. Hi, everyone. 12 people connected. Is everyone in Santiago?
No, we have people from Argentina. The majority are from Chile, but I don't know if we have from other countries.
Okay, perfect. So it's 10 a.m. I'm in Paris. It's 4 p.m.
Okay, it's 10 a.m. in Chile, 11 a.m. in Argentina, 9 a.m. in Colombia.
Okay, so basically people in South America.
Yeah.
Yep.
So Andres is already posted on the chat the Slido for questions, the code. So as we usually do, please make your questions there. And at the end of the presentation of Amira, Andres will moderate the Q&A.
Yes.
Okay, so I'll just mute and wait for people to join.
Okay.
Yeah, but I don't know, Andres, like 2 more minutes, right?
Yeah, 2 more minutes, I guess.
It's
Okay.
roll.
2 more minutes.
Yes. So Paris is still in lockdown or what?
We're still in lockdown. We can't go out until the 11th of May. And
Oh.
so it's been 2 months.
Oh,
We're
yeah.
learning how to live inside of our homes, I guess. What about South America in general?
here in Chile, we don't have like full country lockdown or full city. Some cities, like the south part of Chile, or some, but not all. Like here in Santiago, some districts, not the whole city. But yeah, still people are learning how to work from home and study from home. At least my kids are like getting homeschooling with all the materials from the teachers and everything. It's weird.
But I guess it doesn't really affect us, the blockchain space people, because we're already remote people all the time. So
yeah. Now we have like online meetups. That's the different virtual meetups without like meeting people.
Yeah.
But on the other
That's an
side, it's a good
interesting
thing
thought.
because we can get like good speakers like you, for example.
Yeah, I
Which is
wouldn't
nice.
be imagining myself going to Santiago right now, but definitely online. Yes, hopefully in the future, of course.
Yeah, great.
So we should
okay,
start.
yeah,
Yeah, please.
10:07. Let me give you the option that you can share your screen.
Yeah, thank you.
Okay, so try to share your screen, please, Samira.
Okay, I will. Let me just look for my screens. Okay, perfect. So does everyone see this my screen? I just shared my screen.
Yeah, I can see it.
Okay, perfect. So thank you everybody for joining today. Today's talk is going to be about ZKSnarks. ZKSnark in a nutshell, it means that we're going to talk in deep about the ZKSnark. What does it mean? How do we construct the ZKSnark proofs and how does that work? So just a warning from the beginning, there are going to be some math included. I will try to explain it as simple as I can, but hopefully for those who don't have any, will try to keep up. And if there is any problem, I'll be able to explain when you ask me questions. So to start, just wait. Okay, perfect. So for those who don't know me, let me just introduce myself. So my name is Amira Bugura. I'm a cryptographer. I have a background in mathematics. So I studied and I finished a master's degree in applied mathematics and then did an engineering school in cryptography and cybersecurity, and have been working in the blockchain ecosystem since 2017. So I was working in a research lab in 2017 on morphic encryption, zero knowledge proofs. That's why it's like a topic that interests me a lot. And before starting to work in the blockchain ecosystem, I started then to work with some startups in Paris, mostly as blockchain developer and security engineer. And from 2018 to 2020, I was a cryptographer at Consensus. And at that point, I was working a lot on Ethereum scalability and privacy issues. So I spent 2 years at Consensus, and now I'm free as a bird. So I recently left Consensus, I guess 3 or 4 months ago, and now I'm just enjoying. Well, I'm not really enjoying because of the COVID-19 crisis, but I am enjoying my freedom without work right now. So okay, so as I said, since I have a math background. I'll be talking about the ZKSnarks from a mathematic point of view, but I'll try to be as simple as it is. Okay, so we're gonna talk about the origins of the zero knowledge proofs in general, how it did started, when did it started, is it something that started with the blockchain, does it exist for so long, since when, and why we started using them. Different types of zero knowledge proofs, like interactive, non-interactive proofs, and then I'm gonna speak specifically about and there are some questions on the chat, because I will not be checking the chat, so there will be no questions
don't
like
worry.
for the chat.
Yeah,
for example,
we'll look
like
at it.
Slido. Yeah, okay, just yeah, okay, perfect. So just like to let you know, I will not be taking a look at the chat. Okay, so as I said, let's talk about origins of zero knowledge. So the concept of zero knowledge actually didn't started with the blockchain ecosystem. It existed like since 1985. So 1985, which means that it's been a long time, but they have, except in research papers. And because of the blockchain ecosystem, it's an innovative technology. They have been trying to make use of all the technologies out there, especially in cryptography, that exist and haven't been actually used in this in Web 2.0 systems. So how it started, so three researchers from MIT, Xavi Goldschwager, Charles Rockover, and Silvio Micali, have been working on a mechanism in 1985 to design a notion of knowledge complexity. So what does that mean? It means that they have been trying to prover and a verifier. So a system, we have someone who wants to prove something to another person, a verifier. How much information do we actually need to share with that for a verifier? So they've been studying this knowledge complexity, and of course after that it started the notion of zero knowledge. It means that can we prove something without actually sharing any type of information? So before 1985, this didn't exist, because basically the cryptographic systems at that point were only trying to create systems to allow a certain prover to prove something to a verifier, where they only question the integrity of the prover. So they were always saying that maybe the prover is malicious, so let's make sure we create systems so he or she will not be able to fool the verifier who's honest. So before this time, no one has questions the integrity of the verifier. And so they have started working on this. So again, to explain what do we mean by a proof system? So a proof system means that there is a prover, let's call the prover Alice, who's trying to convince the verifier Bob of a secret or a fact within a reasonable amount of doubt. It means that we're not going to try to explain a certain concept until infinity. Of course, we have a limited amount of time. We're going to try to explain a certain concept, and with a reasonable amount of doubt, it means that the verifier will be certain with 100%, for example, that the prover is telling the truth, or with a certain probability. So that's what do we mean by. Now, every proof system has at least two properties. So here I'm gonna talk about three of those, and every proof system has at least two of those. So the completeness means that every honest prover will always convince the verifier. It means that if we have an honest proof, always the verifier will be convinced. It means that no honest prover is taken as malicious at any sort of time. If we have the right answer, we're always going to be accepted. So that's what we mean by completeness. It means that if someone else comes with a different answer, they will not be accepted. But if we come with the correct answer, we will be accepted. The soundness criteria means that every dishonest prover will fail with overwhelming probability, which means that if we have a malicious prover, they will not be able to go through the process of the proof. That if they were able to do that, it will be very negligible probability. So bringing a dishonest prover with an honest verifier, the probability that that proof will go through and be accepted is very, very, very small. The zero knowledge property means that acquires nothing but the facts that the prover knows the secret. It means that we don't actually need to share the secret with the verifier. We only need to prove that we have the secret, we have the knowledge. So again, to go back to the MIT researchers, before 1985, all research have been done about specifically the soundness criteria, which means that we have a dishonest prover. So if we have that, then we must make sure that this dishonest prover will not be able to go through and be accepted. Now, when they started working, the zero knowledge property has started to appear. Now, I'm going to start explain what do we mean by interactive proof system. So I explained what do we mean by a proof system. Now, how does that actually work? So we said we have a prover and we have a verifier. And now both of them need to share some sort of information to make sure that the verifier will know the truth, whether the prover is honest or not honest. So interactive proof system means that there is interaction between both parties. So Alice, who's the prover, is trying to convince Bob that X number X, sorry, a bit sick. So Alice is trying to prove to Bob a certain information, that X is true, for example. So when X is true, Bob always accepts. That's the completeness property. When X is false, Bob accepts with only negligible probability. So to make sure that that probability is negligible, when we create an interactive system, we make sure that they interact several times. So let's say, for example, Alice is trying to prove to Bob that X is true. And they only interact once, which means that Bob will ask Alice a question and she will answer. So there is a probability of 1/2 that she will give the right answer. She may just imagine an answer, and just by coincidence, the answer Alice gave was the correct one. So she could pass by 1/2 probability. So that's not good. It means that 1/2 probability she will be accepted, 1/2 she will be rejected. And our objective is to make that probability very negligible. So that's why we make the interaction several times. So Bob asks Alice a question first time, she answers. He asks her another question, she answers. And he keeps asking K time, K with K, a big number. So if he has asked her K time, it means that she really, really have a negligible probability to be passed. So it means that 1/2 power K to be accepted. And if K is big, which means that 1/2 power K is very, very, very small. So that's an interactive system. Now, the problem with going back to the case, we have a probability that we have a dishonest verifier. So again, as I said, the soundness property was based on systems that were saying that the prover could be dishonest, and they were creating those interactive systems to make sure that the verifier will be able to get the correct answer, and the dishonest prover will never, or at least with negligible probability, will be able to pass. So it was always assumed that the prover could be the malicious one. these three researchers have questioned the morality of the verifier instead of the prover. Let me give you an example. Let's say you're trying to connect to a certain service online, and you have to write your password to be able to connect to that service. So you are the prover and the verifier is the server. So you're trying to prove to them that you actually have an account on their website and you're trying to connect with your password. So in a normal system, the verifier, meaning the server, is the one questioning your integrity. However, we as well as provers, for example, as human beings using the internet, have also the right to question the integrity of the verifier, the one that's using our private information. So if that server, if that service is malicious, they can use our information, our private information, in a malicious way. So we have to make sure that we share the least possible of information, only to prove to them some sort of proof, but not share more than that. So that's how this started. Now, the problem statement. So we know that we don't want to share a lot of information, but we have two different problems here. So how much knowledge actually we need to verify certain proof? So we're saying we don't want to share much, but how much do we actually need to share in order to make a correct proof? The second problem is, how can anyone make sure, or for sure, that the verifier won't leak the knowledge? Again, as I was saying, so questioning the verifier integrity. So there was a solution. It means that nothing but the truth. Nothing will pass except the truth. So zero knowledge proofs are a subset of proof systems. So with an additional constraints of hiding or zero knowledge. So if you remember the three properties that I spoken about previously, I said that proof system have at least two of those properties, meaning the completeness, the soundness, and the zero knowledge. So the zero knowledge property, it means that we have an additional constraint of hiding information. So a zero knowledge proof is a unique method where a certain user can prove to another user that he or she knows an absolute value without actually conveying any extra information. So that could sound complicated when we read this phrase. So how does that work? And it looks like magic. So can I actually convince someone that I know something without actually sharing anything with them? But it exists. It's not magic. So how does it work? So we have, again, Alice and Bob always in this game. And we're creating another interactive proof, again, with challenges sent by the verifier Bob to Alice, and Alice always needs to send a proof to Bob that she knows a certain information. So for this to work, so Alice computes a proof for a statement and sends that proof to Bob. Bob will choose a question at that point, meaning a challenge, to ask Alice. So that's the challenge phase. We have the witness phase, which when Alice sends a proof, and then we have the challenge phase when actually Bob sends a certain challenge to Alice to make sure that she would answer with the right answer. Now, Alice at that point will calculate the answer for the question and send that answer to Bob. And then he will use that answer to make sure that she answered the right answer. So I'll give you an example, very, very simple example, so you can imagine with me how that can work. So the Alibaba example. If you don't know it, well, now you do. So we have Alice and Bob, of course, or we could call them Alibaba, who's the prover. So she goes inside of a cave, and Bob is standing outside of the cave. So Alice has two paths, A and B. She can decide to go from either A or B to the middle of the tunnel where there is a secret door. Now, she doesn't want Bob to know which path she took. So she decides on her own to go from whether A or B. Now, Bob prepares a challenge for her. Bob wants to know if Alice actually knows the password to that secret door. So that's actually the problem that Bob is trying to solve. Does Alice knows the password to that secret door? So let's say Alice chooses to go by path number A, by path A. And then Bob calls her, tells her, come back from B. So Alice comes back from B. Now, because we know that Alice went from A, of course, she couldn't come back from B unless she knew the password. But Bob doesn't know that. Maybe Alice went from path B and then just came back. Maybe she doesn't even know that password. So in order to make that proof works, they need to do it several times. So Alice, from first time, she goes from A, and then Bob calls her from B. The second time, he may call her from A, then he may call her from B, different times. So the more times Bob calls Alice, the less probability that she doesn't know the password yet she is able to come back. So it just proves more and more to Bob that Alice actually knows the word open sesame to open that secret door and be able to come back. So in this example, we showed that we can actually create a zero knowledge proof. So what do we mean? That we don't share the password with Bob, yet we prove to Bob that we know the password of that secret door by basically sharing nothing, by just answering to the challenge that Bob have proposed. And that's how actually zero knowledge protocols work. So we answer to certain challenges, but the challenge never really reveals the secret itself. So the problem with the types of proofs that I was showing you is that they are interactive. So by interactive, like I said, means there is interaction. Just there is an online interaction between a prover and a verifier, meaning the client and the server. So there is always an interaction between them. It means that both of them has to be online at the same time for that to work. So the problem with this, it doesn't scale. So if we create a certain protocol, and let's say we put it on the blockchain, so we can't make sure that everyone is online all the time, what we need to make a certain proof. So that doesn't really work in the blockchain system. Even though it's a very good protocol and it could work, but just because it's interactive, we actually can't use it. So it's impossible to scale. So we need another solution if we want to use zero knowledge protocols. So what is the other solution? Is to make those zero knowledge protocols non-interactive. So non-interactive, it means that the prover and the verifier do not need to communicate at the same time in order to make such a proof and verify it. So in 1986, after the MIT researchers have started working, Fiat and Shamir have invented the Fiat-Shamir heuristic protocol and have successfully made the entire protocol work without any interaction. So I will not really mention that protocol. You can Google it after if you want, but just to show that there was a certain system and that they were able to make it non-interactive. And how they do that, so this is how it works. So when we have a prover and a verifier, so in the interactive system, we have interaction between the prover and verifier, constructed the proof, sending it to the verifier, and then the verifier has to. We transform all those messages between the prover and the verifier. If we said that they have maybe like 7 rounds of interaction between them, we make them only one message or string, and we send them at once to the verifier. So instead of having all that communication with the verifier, we just put all the messages at once as a prover and send them to the verifier. So we don't really need to wait for the verifier to be online. We just send it and go away. Then the verifier will come back and then verify it. To explain this, so in the ZKP interactive way, the prover generates a request. So they generate a request of wanting to prove something, like the password I said, for example. I want to prove that I have the password to be able to connect to my online account. The verifier at that point chooses a challenge and then sends it to the prover. The prover replies with a response, and then that's it. The verifier will verify that response. In the non-interactive way, the prover starts by generating a request, then computes the challenge. So here you see the difference. In the first example, the verifier was computing the challenge. Here, on the other hand, is the prover who is computing the challenge. So the challenge is the hash of the request and a certain string that we will talk about later on. And then the response, and then send them the verifier. And then they will verify that challenge that was sent by the prover. So what are the properties of non-interactive proofs? So we publish a proof, the verifier publishes a proof. There is a generation of both verification and proving keys. So the proof can be mathematically reproduced by the prover and verified by the verifier. So because we have those keys at any sort of time, we can make sure to verify it again and again. And for example, let's say we are on the blockchain, since we have those proving and verification keys, at any sort of time, we can verify the integrity of that proof. So we need a trusted setup, a common reference string, which can be seen by both the prover. A reference string maybe which is generated by several people that there is a ceremony that's created for this trusted setup to create a certain string that's been shared by the prover and the verifier, both of them. It's used in the challenge to be sent from the prover to the verifier in the initial parameters, and then will be completely destroyed, because otherwise fake proofs can be reproduced. So that's why, for example, in Zcash, not only one person produced that common reference string, but it's several people. This way, when it's destroyed, no single party can reproduce it. So we make the probability of reproducing it negligible when we have several people creating it, and then for only one part to recreate it again, it's basically impossible. So, but I'm not going into details here. Just try to understand that this is the non-interactive way how it works. There is a proof that's generated by the prover and a challenge and directly sent to the verifier, and the verifier will verify the proof. Now, our topic here is ZkSnarks. ZKSnarks are non-interactive proofs. So we have multiple, not only ZKSnarks, we have ZkSnarks, we have bullet proofs. I chose today to talk about ZkSnarks as an example. And of course, we can talk about something else maybe in the future. But in the first part, we have spoken in general about proof systems, interactive than non-interactive proofs, and the difference between both. Now, specifically, we're going to talk about ZkSnarks, which are non-interactive proofs. So let's start by actually decrypting what snark means. It's a very long sentence, but let's try to understand it part by part. So snark actually is an abbreviation of ZkSnarks non-interactive arguments of knowledge. So the first part means that the proof length needs to be short. So do you remember that we said that the prover needs to send a proof to the verifier? So that length of that proof needs to be very, very short. Non-interactive means that it needs to be verifiable in short amount of time, meaning that there is no interaction between prover and verifier. The verifier has only the challenge that's sent by the prover, and they will be able to verify it. So it will be verifiable in short amount of time, just because we don't need any sort of interaction. So the moment we receive the proof, we just verify it. The args, what the arguments of knowledge, it means that need to show that we know an input, certain witness that yields to a certain computation. So again, like what I showed with the Open Sesame example, is that we didn't actually share the password of that door. We only showed that we know the password. So we share a witness. In that example, it was when Alice was leaving from the other side, from the door, from the cave. Here in the online example, we need to send a witness, something that tells that we know the truth to a certain computation. The computation could be a certain function, f equals f of x equals, for example, 4. Do we actually know what is f? So we need to show, for example, that we know f, but we don't want to share what is actually f. So we just show that we know f of 5 equals 4, for example. So that's just a basic example. So I don't actually share the function. F of x could be like x plus 5, x plus 6, whatever, but we don't share it. We just prove that f of 5 equals 4. And maybe the verifier also knows that information, so they will make sure that the information is correct when we send the. And that's it. Now, in order to construct them, so we now understand what the snarks mean. Now let's construct them. So actually, we cannot apply any computational problem directly. So the snarks cannot just say, hey, I have f of x equals something. I'm trying to prove that it's correct. So we can't apply them directly on arithmetic, for example. So we have to convert the problem into the right form for the problem to operate on. So the right form is actually quadratic program. Whatever program we have into polynomials. So we start by creating a program, then we end up by having polynomials, because again, as a prover, you just write in a code. So you write in a code for your proof, then you end up by creating certain polynomials, and on that part, the ZkSnarks will be proved. So the process involves two important steps. The first one is cryptographic proof system for verifying the satisfiability of arithmetic circuit. So actually, we need to create an arithmetic circuit and the cryptographic proof with that. needs to be translated into a polynomial. So these are actually all the processes that we have to go through: computation, algebraic circuits, constraint system, the polynomials, quadratic polynomials, until we arrive to the ZkSnarks. So I'll be explaining each one separately until we arrive to actually what is a ZkSnark. So, warning, serious math. Just joking. I mean, it's not that serious. At least I hope. Okay, so in order for me to explain very, very easily how ZkSnarks work, I chose an example. So we will go through this example from the beginning till the end. So from writing our program until verifying it with ZkSnarks. So, and we'll see how that goes. So the example I took, very easy. We have a function. So Alice wants to prove to Bob that she knows the solution to equation x power 2 minus 4 equals 0. So this is what we want to prove. X power 2 minus 4 equals 0. It sounds very easy, right? It sounds very easy, but it's not that easy when you use zero knowledge. Again, remember, you don't want to share the secret. The secret here is x. We don't want Alice to share what is x, but we just want her to prove to Bob that this equation is correct. So Alice, at first, she creates a program. It could be in Python, it could be C++, or any other language to represent her problem in a code. So this is how we write. So y. So y is x power 2 minus 4. We chose y, but it's equals 0 here. So the evaluation will be to 0. The evaluation leads to y set to 0. It could be a different equation. For example, x power 2 minus 4 equals 5, whatever. Then we just have to make it at the end equation equals 0 to be easier. Anyway, so we start with this program. Everyone's following? I hope. Okay.
Yes.
Yes.
Yep.
Perfect. Perfect. So let me just check. Okay. Yes. Okay. So perfect. Thanks. Oh, sorry, my voice is leaving me sometimes. I'm a bit sick. So okay. So let's move to the second part. Okay. So we have two different challenges. You remember when we were speaking about proof systems, and before zero knowledge appeared, there was always a probability that the prover could be malicious. So this is the second point. So what if we have a malicious prover? So since Alice is the one running the program, because she's the prover, so she will be the one writing that proof, that program. Bob has no control over the code that she runs exactly. So she could cheat, actually. So she could run just the code y equals 0, which would satisfy the condition, because the condition was that the equation equals 0. The equation was x power 2 minus 4, but she could just run a program which y equals 0, and that's it. And it will be verified as true. So we could have a malicious prover. So we need to make sure that with ZkSnarks, we don't arrive to that. So I'll show you how we protect from having malicious prover. Now, the second problem, of course, of why we have actually zero knowledge is that what if we have a malicious verifier? So we need to find a way to allow Bob to get a peek of the value of y at the end of the function without actually learning anything about x, because x is the secret. So Bob can verify that equality of the equation, but he doesn't need to know anything about what actually. Let's start. So now when we take the program and make it to an algebraic circuit. So remember, we had x power 2 minus 4. So we represent x. So we represent a gate. So it's an algebraic circuit. So we represent x multiplied. We have, so both of them are inputs. Multiplied together, we have an output 1. And then we add them to minus 4, and we have another output, which is y. So if we write this in a flattened code, so flattened code, it means that we take our code, we make it to an arithmetic circuit, and then we write it again. So what do we have at the end? So the end, we define f, our function, in a different way. It means that we have now the output 1 equals x multiple by x. We have y equals the output 1 minus 4. So we have written our function in a different way. So why do we need this? I'll show you later why do we need this, but this is the way we're going to write our function. And this is what we call the arithmetic gate. So why I chose this example? Because this example was very simple, and the arithmetic circuit for it was very easy and was not complex. So we just needed 3 inputs, x, and minus 4. So we, for example, when we have x power something, we can't write x power. We have to write x the number of times that it's used. So if x is x power 4, we write x 4 times in order to make an arithmetic circuit. So moving along. So now the constraint system. So our constraint system actually is a triplet of vectors. Now, when we have that flattened code, now we're going to make it a constraint, rank 1 constraint system. So let's define it at the beginning, then we're going to do that. So a constraint system is a list of triplets of vectors. So we have vector A, vector B, vector C. And the solution is a vector S. S will be our secret here. So we create those vectors such that the multiplication of AS vector with BS minus CS equals 0. So here we have a dot product. A dot product means that when we have a vector with a vector multiplied by an integer. Sorry. We define the constraint such way. So we need to find what is actually S. We need to find what is actually S, and we need to create this constraint system in our current system. So how do we do that? So running our program is actually equivalent to finding an assignment of S, which means that we need to find an assignment of S that satisfies the previous equation that I showed, means that equation that equals 0. So we need to find what is S. S is a vector as well. So we need to find that S. So how do we do that? We define S. So how did we do that? So we define that state vector from our flattened code. Now I'm going to explain how. So the elements of the vector are all the variables used in our program. And the solution S will be the solution to each variable. So the variable vector is 1, x, output 1, and y. If you remember with me, when we had our arithmetic circuits, we had all those variables. We had y, we had output 1, we have x, and we had minus 4. So minus 4 is actually, it means that it's minus 4 multiplied by x power 0. So that's why we write here 1. X, it means that we are using, sorry, let's go back. So this is our system. So we have output 1 equals x multiplied by x. Y equals the output minus 4. So these are the inputs that we'll put them in our vector S. So the vector S, we need to find it in order for this to be true. So this is how the vector looks like. Now, find what is A, B, and C, we need to find those triplets of vectors that satisfy this equation. So how can we find them? So we know what is S from the previous equation, and we have to solve this. So to solve this, what do we do? So we write, so we process each line of the flattened code. So we have two lines of the flattened code. Remember, we have two equations. So the first equation was output 1 equals x multiplied by x. And we had y equals output 1 minus 4. If we take everything in one side, we'll have output 1 minus x power 2 equals 0. And here we'll have y minus output 1 plus 4 equals 0. So, as you can see here, x power 2 minus output 1 equals 0 because we took everything in one side. And here the output 1 minus 4 minus y equals 0. So we write the equation to create the constraint system. And we only have the I here is moves from 0 to 2, from 0 to, we have only two of them because we have two equations. So we have A1, B1, C1. So we have A1 and A2, two vectors, B1, B2, C1 and C2 vectors, because we have only two equations. So that's why the I moves between the number of equations. So we solve this and we'll find them. So I'm showing you how I solve this, but actually it's very easy. You can do it by hand. You can solve this system by hand. You just replace with the inputs from S. We know what S equals, the vector S. So we replace each one here until we find the answer. So we find all these vectors: vector A1, B1, C1, A2, B2, C2. So I'll show you how I did it by hand. That's how it looks like. Again, we solve those equations. We replace by the inputs by S, and we have here x power 2 minus output 1 equals 0, and we replace by S, and then we just continue solving till we find those vectors. So you see, even having a very, very small equation as the one I showed you in our example, it takes so much time to actually arrive to ZkSnark. And we're not there yet. So we're not there yet. Now we actually created our constraint system. So our constraint system is those vectors: A1, B1, C1, A2, B2, C2. So this is our constraint system of vectors. Now, if you remember that I said ZkSnarks, we don't apply them on the constraint systems, on the arithmetics, whatever. We only apply them on polynomials. So we need to move from these constraint systems of vectors to polynomials. So how do we do that? Yes, polynomials. So the next step is taking this constraint system and converting it to quadratic polynomials form, which implements the exact same logic, except we use polynomials instead of these dot products of vectors. So the reason we transfer, actually, I'm not really going deep into this, but just understand this way, that the reason why we transform from a constraint system to a polynomial, and we don't, why don't you work with the constraint system and apply the ZkSnarks on them, is to obtain, is that mathematically it's more fruitful to use polynomials, because it's easier from a complexity point of view. It's easier to apply that on polynomials than on constraint systems. So just understand this way. On polynomials, it's easier, it's better, and the cryptographic protocols that we're going to be using afterwards, actually, they need polynomials as inputs, so we can't use vectors with them. So yes. So we start by defining three polynomials, in fact. So again, as we had the vectors A, B, and C, now we have polynomials A, B, and C. where big N here is the number of elements in any constraint vectors. In our case, there were 4. In all vectors we have the 4 inputs, and the small n is the number of equations that we had, which we had 2 equations. So we construct these polynomials by requiring that first polynomial h one, like of the inputs 1, equals the first input of the vector a, which is 0. If you remember the vector a, that's the vector a. So these are a11, a12, a13, a14. Again, b1, b11, b12, b13, b14. So we just replace these in the polynomials. We just replace these, and then we do Lagrange interpolation based on these points to make polynomials. So now you will stop me and say, what is Lagrange interpolation? Or maybe not. So actually, before we move forward, let me just explain what is Lagrange interpolation that we're going to use on these polynomials to find, because our objective here is to find the whole polynomial. So here, we don't know what is the polynomial a, we don't know the polynomial b, we don't know the polynomial c. We just know that the polynomial a at the point and at the point 2 equals this. So we need to find the formula of it, the whole formula, and that's why we use Lagrange interpolation. Let me just see if some people wrote messages. Okay, that's Spanish, sorry. Don't understand it. Okay, so definitely not for me, that message. Okay, now we do Lagrange interpolation. So what is Lagrange interpolation? So again, I'm not going deep in Lagrange interpolation. Everything is available to go through these things. What I'm trying to do here, I'm trying to explain mathematical theorems relation into this. So it's a formula that allows us to find a polynomial which take on a certain values at arbitrary points, which means that I want to find, for example, the polynomial p of degree less than 4, satisfying these equations. So p of 1 equals 1, p of 2 equals 4, p of 3 equals 1, p of 4 equals 5. So I need to find out the whole polynomial, and I only have these 4 inputs. Just one thing. So always, in order for us to construct a polynomial of degree d, we need d plus 1 points to do so. So, you know, very simple example, a line. So we have a line. In order to draw a line, we need 2 points. So if I only have 1 point, I could draw so many different lines, infinity number of possibilities I would have. But if you give me point 1 and the point 2, I only have 1 possibility of that line. So in order for me, for example, when I have these 2 points, to bring back the line to find what is the equation of that line, I need only 2 points, and I'll find it. So, and the line, its equation is only of degree 1, because the line would be x plus a certain a. So in order to draw it, so I need 2 points. So always when we need to reconstruct a polynomial of degree d, here it's degree 1, so we needed 2 points. So here the polynomial is of degree 3, so we needed 4 points. So we need to reconstruct these polynomials. Again, I'm not going to speak about how we do the Lagrange interpolation. Just understand it as a way of reconstructing the polynomials based on certain points that exist on that polynomial that we're going to use to reconstruct it. So you're going to understand it more in our example, in fact, because we needed to reconstruct those polynomials A, B, and C. Okay, so let's move ahead. So So a1 of x is a polynomial of degree 1. So it's written in the way ax plus b. So I just replace by the by a1 of 1. We know that it's equal 0 because I showed it before. a1 of 1 equals 0 because here a1 of 1 equals 0, and here I replaced by 1 because it's 1 here, so the x is 1. So a multiplied by 1 plus b equals 0. a1 of 2, again, I replace, and I just replace all these inputs, and I try to solve these equations. I'm pretty sure it's very easy. You all guys can do it. We studied it in high school, I guess, when we try to solve these equations, when we have a solution to an equation and we try to find it back. So you just solve this system of equations to find back the polynomials. So we find them. We find the a and b for each equation. So we find all these polynomials. So we find all these polynomials and their equation. So a1 of x is minus 4x plus 4. We found the a and we found the b. Again, you could do it yourself and you'll find that, yeah, a is minus 4, b is 4. And you find the solution. So we do that. So when we do that, now we actually can express the constraint system that we had polynomials. So now we replace the polynomials here. And now you're going to tell me what is the h and what is the z. Yeah, we're going to reach that. So we found the a, b, and c polynomials. So a is representing the left input, b is representing the right input, and c is representing the output. Now we're gonna suppose that this equation equals a certain polynomial h multiplied by a certain polynomial called z. What is h and z? We're gonna see here. So, sorry. Yeah. Can you all see what I'm showing, or is this bothering?
Yes.
Is this?
We can see.
I don't know if this is bothering to see the writing.
I mean, we see the slide and your mouse cursor, but that's it.
No, I mean this. It's not bothering, right? I'm moving something here. Okay, perfect. Okay, so now to explain what is the polynomial h and what is the polynomial z. So the prover, Alice, we go back always to Alice and Bob. So Alice computes a polynomial h of x to show a satisfying assignment as to the underlying constraint system. So we can think of that quadratic polynomial system as this portable systems of polynomials a, b, c, and z of this assignment, which is s, as the solution to that equation, which means that actually what Alice does, she computes that h, which solves it. So h, the polynomial h, so she needs to compute it to prove to Bob that she knows those polynomials, that she knows s without actually sharing what is s. Now, what actually Bob does, so to check the correctness, he does not evaluate that polynomial at every single point because it could go to, because the degree of the polynomial could be 2 power 21, for example, and that could be very, very large. So he chooses randomly certain points of the polynomial and verify that it is correct. So he chooses that random points and then divides the polynomial p, which is that a multiplied by as multiplied by bs minus cs A as the polynomial, S is the vector. Yeah, so again, the same system. So P is that polynomial that verifies the equation. So he takes that polynomial P and divides it by Z. And if you remember, I said that P, this polynomial, equals H multiplied by Z. So if he divides by Z, he will find H. And since Alice would compute H and send it to Bob, so if he divides this by Z and finds something that is different from what Alice says, it means that Alice is not given the right answer. So you see where we arrived? We arrived at verifying this polynomial instead of actually sharing what is as the secret. So he shares that the division actually has no remainder, because if the division has no remainder, it means that the solution to that P divided by Z is an actual polynomial that exists, which is H. Now, moving forward. So again, if you remember, I said Bob will evaluate at some points, and he will not evaluate the polynomial P at all the points. So when he divides P by Z, so he chooses random points to evaluate on them. So if the prover, Alice, knows in advance which points Bob will choose to check, she might be able to craft polynomials that are invalid, but will still satisfy the identity at that point, which means that she could randomly choose a polynomial H, which is not the correct H that verifies the equation, but again, it still verifies the equations, but again, it's different one. So she's not really answering the right question, but she knows which points he will choose. Then she would know which answer she could give, fake answer she could give to answer correctly. So that's in case she would know which points he will choose. Now with ZkSnarks, we actually use different techniques to hide this point that will be chosen by Bob. So Bob will be able to choose a point and will never tell Alice which point he chose, yet he will be able to evaluate at that hit points. So how does that work? We can use techniques like homomorphic encryption and pairing over elliptic curves to blindly evaluate over polynomials. So for example, because we have a polynomial and then we need to choose a point to evaluate on that polynomial. So if you can imagine, you would say, well, if Alice doesn't know which point Bob will choose, how can she respond to the challenge? So she needs to know what challenge he gave her in order for her to respond, right? But yes, she can answer even if she doesn't know the point. And again, I said, why would he hide the point? Because he wants to make sure that Alice will not give a fake answer if she knows in advance that point that he will choose. So how would we do that? As I said, using homomorphic encryption and paired over elliptic curves. So these techniques maybe you have heard of, maybe not, but I'll explain each of those and say how we use them in ZkSnarks. So starting by homomorphic encryption. So homomorphic encryption schemes, so there are a type of encryption that have the homomorphic property. So what does that mean? So again, homomorphic encryption, it's an encryption scheme that allows computation over ciphertext, which means that we have an encryption scheme. We encrypt, for example, I'll give you an example, the addition. So I have F, and then I have X1, and I have X2. And I want to compute F of X1 and F of X2. And I don't have the resources to do that. So because homomorphic encryption is basically used in cloud computing, for example. So I want to compute that, but I don't have the calculator, for example, and someone else has the calculator. I don't want to give him my X1 and my X2, but I want him to give me the response to my questions. So I want him to give me the addition. So how can he do that if he doesn't really receive my X1 and my X2? So homomorphic encryption allows that. It allows us to have the homomorphic property. The homomorphic property, it means that F of X1 plus f of x2 equals f of both x1 plus x2. So if we have here, for example, the encryption of M1, which could be any the homomorphic encryption, and the encryption of M2, and by evaluating means that we have C3, and if we decrypt C3, we actually find that it's the same as if we applied the evaluation over M1 and M2. I hope you're following with me. It's like the operation that we want to operate over the plain text, even though we actually shared the ciphertext. So in Bob's case, he doesn't really want to give to Alice the point that she chose, but he wants her to be able to use that encryption of points that he sent her and be able to use it inside of her polynomial and the response back. So I can give you an example of RSA. I don't think I left the RSA example, but yeah, anyway, I don't know if I can explain just by my hands, but the RSA, it's an encryption system and it's an homomorphic encryption system. So RSA, the equation of RSA is M, which is the plain text, power E. So if you want to do the homomorphic property for RSA, for example, so we have two plain text, M1 and M2, and we have since we want to encrypt them, so we use the same E because E is the encryption key. So we have M1 power E and we have M2 power E. Now the encryption of M1 multiplied by the encryption of M2, so we applied a certain function over this ciphertext, so is M1 power E multiplied by M2 power E. And actually it's the same as saying M1 multiplied by M2, both of them power E. And that's actually as if we put the compute the cipher, it will be M1 multiplied by M2, both of them power E. So again, RSA, as other encryption schemes, they have the homomorphic property, which means this homomorphic property would allow us to not to reveal the text that it's inside of the encryption, yet we'll be able to apply certain functions over it. And it would be is the same as if we applied them over the plain text itself. So how is that good? It protects privacy. So for example, in the cloud computing example, it protects privacy for the person who wants to ask for a service from the server, for example, who has the computation power, and yet receives an answer for what they're asking. From the verifier to the prover. Now, I said there are two techniques that we use in the ZKSnark. We have the elliptic curve pairing as well. So the elliptic curve pairing, you can imagine it as a one-way homomorphic encryption that we do a quality check. So what do we mean? It means that one way, it means that we can compute f of x, but having f of x, we cannot have x back. So it's the same one-way property that we have for hash functions. So hash function, we can compute the hash of a certain string, but we cannot find that string back from the hash function. So we use them as one-way homomorphic encryption that you can never decrypt. So having the encryption, you don't have to worry, you can never decrypt it. However, for example, with the homomorphic encryption part that I the homomorphic hidden properties that we will use in the ZkSnark. So the prover has access to some function, f, with the following properties. One way, it means that we can compute y, which is f of x,
but given y, we can never find what is x. Linearity, that's the same thing that I was telling before. F of alpha x plus beta y is the same as alpha f of x plus beta f of y. Again, the example that I gave, we had, for example, multiplication here, and alpha and beta was equal to 1. So f of x multiplied by y was f of x multiplied by f of y. So that's a morphic hiding property. Is never equal to f of y. So that's good, which means that even if the prover choose a different input that verifies still the equation, but it's different from that, that never really works, because if they choose a different input, it would never verify the equation if it's not the right input. So ZkSnark in action, how can we actually apply that in the ZkSnark? So the practical ZkSnarks that exist today use pairing-based cryptography. So the pairing-based, the one-way homomorphic encryption function. And that function is known by both the prover and the verifier. So it doesn't really matter if you know the function or not. What we really want. So this is how it works. Bob chooses a point x0 randomly, at which he wants the polynomial p to be evaluated. So remember the polynomial p, it was the polynomial a multiplied by s, the vector, multiplied by b multiplied by s minus c of multiplied by s. So that's the polynomial p. And he wants to evaluate that function f of x0 equals z. And he sends that z to Alice. Now Alice computes p of z. P of z is p of x of x0. And so she computes that, because of the linearity property, she will be able to do this. So p of x of 0 is actually f of px0. And then Bob, how can he verify? He takes p of z computed by Alice and compare it to f of p of x0. He doesn't know. Sorry. So he doesn't evaluate the p at all the points. He only evaluates it at this x0 and maybe other points as well. So if the two results match, then Alice, then Bob is certain that Alice is telling the truth and that she knows the polynomial p that Bob is choosing. It wants to evaluate the point at. So basically, that's it. That's it. Well, not really that's it, but that's how ZkSnark work. I could have gone more into details, but I prefer to give the example that we started with. So just for you to understand kind of the key points that the ZkSnark starts. So the homomorphic encryption, the pairings, what is the quadratic equations, and the flattening of code. So all these things, we have to go through them in order to create a ZkSnark code. I haven't talked about the coding part. I basically talked about what is the math behind it, but that was a choice. I hope you liked it, and thank you. Yes, so I
Wow.
finished.
Great.
Amazing.
Thank you. Yeah, I mean, well, okay, we have a couple of minutes for questions. There's not many. First of all, thank you, Amira. It was great. And
My pleasure.
And for the rest of us, if you didn't get anything, we still have this recording, so you can watch the recording later and see.
Yeah, and I can send the presentation as well. I'll add some links, some references, and send the presentation so you can put it on the Meetup website. This way people can look more if they're interested to understand more how it works.
Perfect. Thank you. Okay,
Perfect.
so I guess the first question is what are ZkSnarks? I guess it's explaining through all these. Okay. Question: how did you get into crypto?
Is it me, or is it a question
it's
about me,
you.
or how did
Yeah,
ZkSnark
it's
want
about
to go to
no, it's
crypto?
about you, I guess.
Okay. You mean
I think they're asking like in
what crypto do you mean?
crypto world, not in cryptography specifically.
Oh,
Because
well, actually, when I was studying cryptography, we had a course about blockchain. So here in France, in my engineering school, a teacher of mine, he loved the blockchain and he was always talking about it. So we had that course when we didn't really start with the cryptocurrency word. I mean, of course, he talks about Bitcoin, but not as a cryptocurrency. But he basically talks about the blockchain behind it and what are the cryptographic methods that are used. So we started being interested in this field, me and others, for other students in the class as well, because we saw the potential of like everything that we were studying and we were using in research labs and was never used in campus, only in research labs, just because the efficiency of those protocol is not yet on a product level, but it was only used in the blockchain. So if you're interested in research and want to continue like working in cryptography, blockchain is the place for it. So yeah, so that's why.
oh, nice. Okay, we got a question from Matthias. What is the current state of the Aztec protocol, ZK protocol on Ethereum?
Sorry?
What is the, do you know what is the current state of the Aztec protocol?
Of the Aztec protocol.
Yeah.
I think I just saw like they put something on Twitter. So I don't know the current state of their protocol. I think they were using the Planck. I'm not sure. I haven't followed them for a few months, so I don't want to make mistakes. But again, like Aztec protocols, they were using a lot of morphic encryption. I don't think they were using ZkSnarks. I think because they have started working with the Planck, which is also like our different proof systems. But again, yeah, I can't really give an answer because I'm not sure. But it's interesting. Like their work is also interesting.
Mm-hmm. Okay, can ZkSnarks be used for online voting? I guess to keep the secret of the vote.
Of voting, yes. So one of the, of course, like ZkSnarks. So the idea is to hide certain information and to be able to verify it. So you can just leave it to your imagination and imagine all the use cases that you can do for it. Of course, voting could be one for it. But I've seen like people, especially in the blockchain ecosystem, have been ring signatures in the voting system. So because so it depends, like what do you want? Like, do you only want to hide what you voted, or you don't want to show, for example, who voted? So for example, like ring signatures, you have a set of people which is like a community, and one person of that community can vote, or for example, and you never know who voted, but you'll be able still like to count that vote. So if it's a yes, so you can count it in the system, but you don't really know who voted from that community, because ring signature is like it's like a ring, and like one of those people would vote, but you never be able to trace back who from that community. So it's very good for hiding the identity of the person. Whereas if you just want to hide what you voted, but I guess, I mean, if you want to hide what you voted, but yet you want to count the vote, you can.
again, with use of homomorphic encryption. So you don't really know what's written, but you can still count it and use it. So yes, you can. Sorry for the long.
No, great,
But
great.
if
I guess
this-
we're gonna need to have another
who asked the
session for
question?
signatures. I don't know. It was anonymous.
Yeah, so if you're interested, the person who asked, if you're interested, check also the work that's been done with ring signatures as well, especially in the voting. It's interesting.
Okay, nice. Okay, so Patricio here asks, as far as I know, ZkSnark is for equation. For inequations like x greater than n, is valid proof better?
I'm sorry. Let me
Okay,
put
I don't get the
louder.
question. Yeah, okay, the question is, as far as I know, ZkSnark is for equations. For inequations, like x greater than n, is bulletproof better?
Is valid proof?
Bulletproof better?
Ah,
Yeah.
bulletproof. For
Or-
actually, so yes. So when you it depends also like on the equation. So you have, for example, like ZKSnarks, where you have like an equality. So you have an equality and you want to prove that equality. So definitely ZkSnark is better. Bulletproof actually is good like when you have like, for example, like not sure of the, for example, like x is less than y, so you want to prove that x is less than y, so bulletproof is much better for that. So you have a range, but also like range proofs, yeah, like for example, like because bulletproofs, I think that, yeah, they use range proofs, I think. Yeah, right, I think yeah, they use range proofs. So I have to check on that, but I think so. I think they use range proof, and range proof is like when you have like it's like you have x and y, and x is less than y, you have to prove that it's in a certain range. So it's in a certain range, you're not sure what is the actual value, but you are respecting that range of that x minus y is less than 0, for example, something like that. So you're respecting that range. So it's better for this.
Okay, great. So what's the better source for news from cryptography for dummies? Twitter.
Well, it depends. I mean, I've seen recently that, for example, like Blog Geeks, they have really cool courses, one-on-one courses for blockchain, and they also have like some for cryptography, and they're really good. But I don't think they go to details. Like when you say cryptography for dummies, you mean like initiated to public key encryption and stuff like that. So
Yeah, I guess so.
like Google it, you'll find like so many things, like so many presentations, one-on-one cryptography that could be useful. But I also advise like Blog Geeks, search on Blog Geeks, they have cool stuff.
Awesome. Okay, last questions because we're running. Are the ZkSnark used now? What is the best use case? We lost you.
Well, like until now, I still haven't seen a better usage than what Zcash, for example, is doing. I mean, there have been so many different ideas, but a private transaction by far has been the best so far, in my opinion. Zcash, of course, they're using ZkSnarks, and I think it's a really good use case for the snarks, private transaction. ZkSnark, for example, they're used for solving a lot of scalability issues on Ethereum. So ZkSnark is a different system. They're more used to solve scalability issues on Ethereum. ZkSnark as well can solve scalability issues because the idea of having to prove something without actually proving it could take a lot of the work out of the miners, for example, that they have to verify every single smart contract all the time. Well, if you create zero knowledge proofs for them, they just have to verify something that will prove like that big group of like proofs is true. So we create like, for example, like a Merkle tree of proofs, and they only verify that instead of verifying everything. So that could help a lot with the scalability issues. So that's another use case I see it.
Okay.
And I think
Great.
Snarks are better for that.
Well, again, thank you, Amira, for hosting this. And
Yeah.
I guess we will share this and the record and everything. So thank you again.
Thank you everyone, and sorry, lots of math. I hope we were able to follow.
No, that's fine. That's fine. We need to know about this. It is important.
Yeah, I always say that no one actually speaks about what's behind the curtain, what's behind the scenes, what's happening actually in the ZkSnark. They're only saying proofs, how actually that proof is constructed. So it's nice from time to time to actually understand the complexity of it, to appreciate it more, and to understand more if you want to code it, for example.
Yeah, definitely.
Perfect.
Well, thanks to everyone that shared with us this presentation with Amira. As you know, we have our Twitter account, Ethereum STHO, Ethereum Santiago abreviado. And we have our Telegram channel, Ethereum @Santiago, available. This was recorded online in our YouTube channel. So if you want to review from the beginning, just ending this webinar, you will have available in the YouTube channel. So thanks again, Amira, for your time, your participation. Thank you, Andres, for let us the opportunity to have Amira also. So have a great afternoon, Amira, and great day for everyone else.
Thank you, everybody. Bye-bye.
Bye.
Bye.
Thank you.
Bye-bye.